Hi students, myself Tanmoy Datto, Assistant Professor, Department of Chemistry, JS College of Engineering, welcome you all in my fourth lecture of thermodynamics. You know, in previous class we already discussed about the basic concept of the thermodynamics. We discussed about the some basic terms of the thermodynamics like system, like process, the different kinds of properties. Okay, so that all the things we discussed. We already discussed about the first law of thermodynamics, and we discussed about the its numerical problems. We discussed about the its molar heat capacity, okay, under constant volume and the constant pressure. We already discussed about the drawbacks of the first law. Today we will discuss about the, first of all, there are two types of process are there. First one is the exothermic process. And second one is the endothermic process. Okay, so we'll discuss about the exothermic and the endothermic process, because these two processes are very much depending on the delta H value. You know delta H, what is the delta H? Delta H is the change of enthalpy. We already discussed what is the enthalpy change. Okay, so exothermic and the endothermic process. Okay, endothermic process. So now we will discuss about the most important topic of the thermodynamics, that is the second law. Okay, we will discuss about the second law of the thermodynamics. Okay, then we will discuss, obviously we will discuss about the entropy, the most important, another most important topic of the thermodynamics. This is the entropy. Okay, then we will discuss about the Gibbs free energy or change of Gibbs free energy, and obviously we will discuss about the with respect to delta G, how we can determine the spontaneity of the system. That means either system will be spontaneous, either it will go to the forward direction or it will go to the backward direction. We will discuss from the value of the delta G. So that all the things we will discuss today, and with that obviously we will discuss today some numerical problems which are very important, because without numerical problem we can't imagine the thermodynamics. So you have to solve the problems also. Okay, so these all the things which we will discuss today. So let's start the class. So first of all, look here, if we consider that exothermic and the endothermic reaction, then we have to draw, first of all we have to draw such kind of curve. Curve means, you know, in the in the y axis. Okay, so y axis it represent the energy. Okay, so it represent the energy. Okay, and the in x axis, look here, in the x axis it represent the reaction coordinates. Okay, so x axis represent the reaction coordinates. So if it is the exothermic reaction, then the curve will be like this. Okay, so now it is the reactant, actually it is the R for reactant, and it is the product. So now from the graph, look here carefully. This is the activation energy, all of you know very well. Okay, this is the thing of the kinetics mainly, but here I am discussing because there is a role of the delta H, that by which we can understand the reaction will be either exothermic or endothermic. That's why we are discussing again, I am discussing again the thing of the chemical kinetics in the chapter of the thermodynamics. Okay, so now look here, if you consider the reactant here, if you consider the reactant, then look, reactant is here but product is here. Okay, so from these two, if you write down that change of delta H, so obviously delta H equal to what we can write down, H of P, enthalpy of P minus H of reactant, isn't it? This is the normal case change of delta H. Okay, so here look here, that H of R, that means reactant enthalpy, that is greater than product enthalpy. Why? Because look here, that here here it is the reactant, so reactant is much higher. If you consider this is the y-axis or the energy axis, or if energy means it is here the heat content, actually heat content we are considering the energy axis, and if it is the product axis, then if you look carefully, then look here, if delta HR greater than HP, that means if you think carefully, then we from there we can write down delta H equal to negative value, and this is the graph for the exothermic reaction, this is the graph for the exothermic reaction. Okay, so where it is mentioned in the question, or if the value is mentioned in the way that delta H equal to negative value, so you have to take it as the exothermic reaction. Okay, so keep in mind that for exothermic reaction delta H value will be negative. Now if we come to the second type of process, that means if we draw the curve for the endothermic process, then you will see if it is the endothermic process, then obviously here in the y-axis this is the energy, and x-axis this is the, again it is the reaction coordinate. Okay, so if it is the reaction coordinate, then you will see that if you draw the curve for the endothermic reaction, then look here, endothermic reaction curve will be like that. Okay, it will be like that. Okay, so here in endothermic reaction it is the reactant and it is the product, and in the same way, you know, this is the amount of activation energy which is required for the reaction. But in the case of activation energy we are not interested here, because this is the case of what I told you, chemical kinetics. We are considering only in the case of delta H. Okay, so because this is related to the thermodynamics part. So in the same way, if we want to calculate that what will be the delta H here, then just write down same way, H product minus H reactant, isn't it? So but here look here, delta H H for product that greater than H for reactant, isn't it? H for product is greater than H for reactant, because here H for product and here it is the H reactant. So H product obviously it very greater than H reactant. So if H product is greater than H reactant, then we can write down from here that delta H value, it will be delta H will be positive, isn't it? So look there, how interesting is this? This is the case of endothermic reaction. This is the case of endothermic reaction. So how interesting is that for endothermic reaction, from the value of delta H only we can predict that what will be the reaction, either delta H will be positive or negative. So what is the conclusion? The conclusion is here that for exothermic reaction, delta H will be negative value, and for endothermic reaction delta H will be, it is the positive value. So you have to keep in mind these two facts, because this is very important to understand either the reaction is the exothermic reaction or the reaction is the endothermic reaction. Okay, now we will move to the second law of thermodynamics. Okay, so what I told you that in case of second law of thermodynamics, in case of that I told you in the previous class that there are some drawbacks depending on which we are getting the second law of thermodynamics. Okay, so what are the drawbacks of the first law? I again repeat, the main drawback of the first law is that in the first law there it is not mentioned, here it was mentioned that energy can flow, energy can be converted, or heat can flow, but there it was not mentioned that direction. Okay, so in which direction heat will flow or energy will be converted. Okay, so that direction was not mentioned in the first law of the thermodynamics, and depending on this fact, actually the second law of thermodynamics came to the field. So now what is the second law of the thermodynamics? So in the second law of thermodynamics, most simply I will tell you simple definition at first, then I will tell you that what is the quote unquote the definition of the some scientist. Okay, so first of all, according to the second law, that tells about this, that heat always flows to the down to the hill. Okay, it always flow to the hill. Okay, down to the hill. That means, what is the meaning of this fact? This indicate that heat always follow or flow, heat always flow that high temperature down to the hill means it always flow high temperature to low temperature. So that means heat always flow that high temperature to low temperature. It is the very general form of the second law of the thermodynamics. Okay, now I will tell you that according to the name of the scientist, there are some statements according to the name of the scientist. That means there are some scientists who produced the second law of thermodynamics in different way, and most common or most famous, the statement for the Clausius statement. So what is the Clausius statement? Clausius told that heat by itself it cannot flow from the from low temperature to high temperature. It is the Clausius statement. Okay, low temperature to high temperature. Okay, so low temperature to high temperature heat cannot flow by itself. Okay, by itself. That means heat can flow from low temperature to high temperature only when if there is some application of some external energy. Okay, if there is some energy of any other device or some external energy, if any kind of energy is applied on the machine, okay, then only heat can flow from low temperature to high temperature. I can give you one example, that AC, okay, air conditioner. You know, air conditioner act in the different way, isn't it? So this is the machine where electricity is supplied. This is the external energy which is supplied by the external agency, and that's why heat is flowing, or heat flow from low temperature to high temperature. But according to Clausius, by itself, if there is no application of any other external energy, then by itself heat never flow from low temperature to high temperature. Okay, so this is the most simple way by which we can define the second law of the thermodynamics. There may be another way also, that the heat cannot be completely converted into work in a cyclic process. It is the Planck-Kelvin statement in this way also, or without any application of external energy, heat cannot be flow from low to high temperature. Heat always flow down to the hill. So there are several kinds of definition or statement, but inner meaning of each and every definition will be same, that heat always flow to the down to the hill. That means it flows to the high temperature to low temperature, and this is the second law of thermodynamics. Okay, now come to the most important part of the thermodynamics, most important topic of the thermodynamics, and this is called the entropy. Okay, so entropy generally, this is there's a common phrase like that entropy cannot be determined. Entropy cannot be defined. Okay, so it cannot be defined in one sentence. Okay, so we have to understand what is the entropy. So what is the entropy? Entropy, it is a measure of the randomness or the disorder of the system. So I can tell you that what is the meaning of disorder of the system. Disorder means that for example, if you think about solid, liquid and the gas, then what you understand, that solid to liquid there will be the distance between the atoms will be increased, and liquid to gas, again the distance between the atoms are increased. Okay, so this, when distance between the atoms are increasing, this is called the randomness of the system will be increased. In case of solid, it is more compact, but in case of your liquid or in case of gas, gradually the randomness increases. So entropy in this way it can be measured. Okay, but we can't define the entropy in one sentence. It is a measurement of the randomness of the system. Okay, so greater the randomness, look here, greater the randomness, higher is the entropy. So what I told you, if you think about the solid, liquid and gas, then obviously the entropy of the gas will be more higher than entropy of the liquid, than entropy of the solid. Okay, so with increasing the entropy, or with increasing the randomness, the entropy will be increased. Okay, entropy change during a process given by then delta S equal to S2 minus S1, that means the S product minus S reactant. Okay, so S product minus S reactant. So delta S is related to the, you have to keep in mind this fact, delta is related to the T for a reversible process as follows: that delta is equal to Q reversible by T. This is very important fact. The change of entropy that equals to delta Q reversible change of, that means that related to Q and T, that obviously it is in the reversible process. That fact you have to keep in mind. Okay, so in a particular process, you know that delta S total equals to delta S system plus delta S surrounding. Okay, so delta S system plus system minus surrounding equal to delta S total. Okay, so that means what is the change of the delta S, we can understand in this way, and total delta S equal to that delta S system plus delta S surrounding. What I told you, if it is greater than 0, that means at the equilibrium entropy of the system is the maximum and it is the delta S equal to 0. For irreversible process, you have to keep in mind, for irreversible process, the delta S total equal to delta S plus delta S system plus delta S surrounding greater than equal to 0, and obviously delta S total equal to here delta S system plus delta S surrounding. Okay, delta system plus delta surrounding, and if you want to calculate that what is the delta system, then you can understand that you can write down that delta S system equals to delta S total minus of delta S surrounding. Okay, so in this way you can also calculate the delta S, what will be the delta system. Okay, so now you have to keep in mind that at equilibrium these facts are very, very important, which you have to keep in mind, that for equilibrium delta S equal to 0, and for irreversible process obviously delta S total greater than 0. These facts also you have to keep in mind. Okay, so now come to the another important topic, that this is called the spontaneity. Okay, so what is the meaning of the term spontaneity? So spontaneity means a spontaneous process is an irreversible process and may only be reversed by some external agency. Okay, so any kind of spontaneous process is an irreversible process, that should be irreversible process, and may only be reversed by some kinds of external agents. The tendency for a process to occur depends upon the two factors. Okay, what are the factors? The first factor is that tendency for minimum energy, tendency for maximum randomness, and the result of the above two tendencies, which gives the overall tendency for a process to occur, is called the driving force of the process. Okay, so these two are mainly driving force of the process. Okay, so spontaneity is very, very important. You have to understand properly what is the spontaneity, because depending on the spontaneity there is a next term or next topic which is very much important, and this is the Gibbs free energy. Okay, so you have to understand what is the Gibbs free energy. So Gibbs free energy is that the available amount of energy to the system during the process which can be changed into useful work. Okay, so the available amount of energy to the system during the process which can be changed into the useful work, this is called the free energy of the system. Gibbs free energy helps, this is very important, that actually Gibbs free energy gives us the information about the spontaneity of the process. So if the delta G value, that means the change of Gibbs free energy is negative, then the process will be the spontaneous. If it is the positive, the process will not be spontaneous. But how or when delta G will be negative or when delta G will be positive, is there any responsibility for the other terms which is responsible to such that we can get the delta G negative or delta G positive? Then we'll understand this equation. This is called the Gibbs free energy equation. Delta G equals to delta H minus T delta S. Okay, so what is the delta G, delta H, you know, this is the change of the enthalpy, and you notice the temperature, and delta S, change of the entropy. Okay, now this we already discussed about what is the entropy. Entropy means the change of randomness, and you know that when delta S will be positive, that means if entropy positive, then the system goes to be more random. Okay, system every you know, in our universe every system has a tendency to increase its randomness. Like for in our case also, if we go to a playground, we'll feel more happy than if we in a particular room or in our home. Okay, if we go to the playground, if we get the open space, then we can move here and there, it is more comfortable for us. So this is also that randomness. Okay, so with increasing that overall our universe, the entropy is increasing. Okay, so every system has a tendency to increase its entropy. So like this also, if entropy will be increasing, then obviously there will be an increase of the their system. Okay, system randomness. Now come to the fact that to decrease the value of Gibbs free energy process, we have to consider this equation. Now when it will be positive, when it will be negative, according to this Gibbs free energy we have to determine. Now namely that here there is two factors which are present in the equation. One is the delta H, another is the T delta S. Okay, so we have to consider one by one what is the delta H and what is the T delta S. So if you consider the delta H, then it is a change of enthalpy, and T is the fixed, and delta S is the change of entropy. So now come to the point that if delta G is negative, this process is the spontaneous, I told you. If delta G is 0, this is very important, that the process does not occur or the system is in equilibrium. Okay, this is also you have to keep in mind. If it is in equilibrium, then delta G will be 0, and I told you if delta G positive, the system is the non-spontaneous, or system does not occur in the forward direction, it may occur to the backward direction. Okay, the reaction will not go to the forward direction, it will come back to the backward direction. Okay. So now here look here is a table also. Look here, that if we consider the equation, then when it will be the positive, negative, or the like if you think about the delta G value here, then that table indicate that when or which value depends on the spontaneous or non-spontaneous. Like if delta G value, if you know, if delta G value, if the equation is the delta G equals to delta H minus T delta S. Now look at the equation. Okay, so in this equation delta G will be negative if delta H is negative here and delta S is positive. So if delta S positive here, then obviously T delta S will be positive. Okay, so if T delta S will be positive and delta G will be negative, then obviously the delta J will be each and every time it will be negative. Okay, so there is no scope or no condition that no case, such kind of case arise that when delta G will be positive, because both the terms delta G negative, so here negative term comes, and also T delta is negative, so negative obviously negative. So system will be spontaneous at all temperature. Okay, system will be spontaneous. Okay, second case, look here, if delta H is negative, then it will be negative, delta H will be negative. But if delta S is also negative, then what happens, this value will be the negative, and negative there is a chance of positive, but that depends on the temperature. If it is very low temperature, then what happens, this value will be lower with respect to the delta H. At that moment it will be spontaneous, because at that moment delta G will be negative. So if low temperature, if the temperature is very low, then if even delta is negative, the process, because I told you that every system will be the tendency to be the to increase its spontaneity. So it is expected that the delta S will be in each and every case, delta S will be positive, because delta S means delta entropy of the product minus entropy of the reactant. So if the entropy of the product will be higher, then there is a chance that delta S will be positive. But here, look here, even delta is negative, okay, but at low temperature the process may be spontaneous. Okay, the third case, look here, that if they both are negative, then high temperature there is a high chance of the non-spontaneous, because at high temperature then this will be negative value very high, then negative will be, it will be positive, then when it will be positive, then there is a high temperature, it will be non-spontaneous. Okay, so now they come to the third factor. Okay, if we consider the third factor, then look here, that if here you can get look that if delta H is the positive and delta S is the positive, okay, both are positive, then again the delta H is the positive, and obviously there delta S is also positive. Delta S positive means this is the negative value. Okay, if this is the negative value, then what happened, then low temperature it is spontaneous. Okay, even at high temperature also it can be spontaneous, because at low temperature at very low temperature, what happened, it is a chance of non-spontaneous also at low temperature, because here it is the positive value. So at low temperature it is the it is actually non-spontaneous, it is not the spontaneous, it is actually non-spontaneous at low temperature, because here look here, because if it is low temperature, very low temperature, then what happened, that this value will be this value will be positive. So positive means it will be negative, but negative value is very low due to low temperature. So if the delta H value is the positive, then it will be greater than T delta S, then delta G become positive, so it is the non-spontaneous. But if the temperature is very high, then opposite case, then there is a chance of the spontaneous. In the same way, if the delta H is the positive and delta S is the negative, that at all temperature it will be non-spontaneous. Why? Because here negative it becomes the positive side, so there is no scope of getting the delta G negative. So this table is very important. At all temperature will be negative, so very important. You have to keep in mind that there may be some kinds of MCQ question arise from here. So this table, that's why you have to keep in mind that when it will be spontaneous, when it will be non-spontaneous, what is the delta G, change of Gibbs free energy, etc. That all the things you have to keep in mind. So now we will move to some numerical problems from this chapter. Okay. So this is a sample question. You can take it as a sample question, because here, look here, that in this question what informations are given here. I'll give you the information what is available. So here in the question it is written that 7.4 gram of argon, okay, 7.4 gram of argon that occupy the 17 liter at 300 K. Okay, so this is given. Okay, 300 K, this is given in the question. There are two questions are given, that at isothermally. So I'll give you the first question, then second question. At isothermally, if the gas expand, okay, if the gas expand 3 liter against a constant pressure, what is the pressure? Pressure is also given against a constant pressure, that is the 700 atmosphere. Then you have to calculate what is the work done for the system. Then you have to calculate what is the work done for the system. You have to find out what is the work done for the system. So look what informations are given here. So first of all, 7.4 gram, this is the amount of argon at first of all 17 liter at 300 K. So this is given. So then isothermally against a constant pressure, that means irreversibly. So first of all, irreversibly it expand up to 3 liter. Okay, irreversibly it expand up to 3 liter at against 700 atmospheric pressure. Okay, 700 atmospheric pressure. Then what will be the work done? So how we can calculate? So we can write down simply that W equals to that W, that is the work done. Obviously it is the irreversible process, So W irreversible equal to, you know, this is the minus of P ext. This is minus for the expansion work. That is a simple case. This is the sign for only that reason. Delta V. So here Pxt means it is the minus 700 into expansion is the 3 liter, because it is mentioned in the question that expansion occur 3 liter. So then what you will get? You will get it will be minus 2100 liter atmosphere. So this is the answer for the question. Okay, so this is the answer for the question. And then there is another question. Okay, so what is the another question? The another question is that the information is the same, but here in the second step, here it is mentioned it is not the irreversible, it is second step, it is a reversible, because that's why it is mentioned in the question that it is expanded that against not constant pressure, against variable pressure. It is mentioned in the question against variable pressure. And if it is against variable pressure, then what happened? Then in the second step, it is mentioned in the question that what will be the work done against it is expand against the variable pressure, where the molar mass of the argon is given. Okay, so molar mass of the argon, molar mass is given. This is the 39.95 gram per mole. Okay, so this is given in the question. So then you have to calculate the work done. That work done, the expansion occur isothermally, and obviously variable pressure means it is the reversibly. You have to find out the work done. Okay, so how you can calculate this? Okay, let's look at here. So first of all, what is the equation for the reversible work? We can write down for the equation for reversible work in this way, that W reversible, that equals to minus n at t ln, it is the V2 and is final by initial, or V2 by V1, isn't it? So now what is the, first of all you have to find out what is the N. So N equals to, it is the number of moles. So here it is given that 7.5 gram argon present and molar mass 39.95. So what will be the value? We have to take the value as the N, and R, you know what is the R? R is the universal gas constant, so take it the value as the liter atmosphere, because we are calculating in the liter atmosphere. So 0.082, it is the liter atmosphere Kelvin inverse mole inverse. Okay, so this is the value of the liter atmosphere. Okay, then next you have to find out, you have to find out that what is the V final. V final equals to what will be the V final V2, what it is the V2. So V2 equals to 17 plus 3, that equals to 20 liter, and the V1 that equals to 17 liter. Okay, so all the values are known here. Okay, in R, and what is the what is the T? T is the 300K. So T is the 300K. So all the values are given here. Just you have to put the values, all the values properly. Then you will find out that W reversible equals to minus 0.74 liter atmosphere. This is the result for the problem. So this type of problem you have to practice a lot. I will give you the assignment also, the overall question paper of the thermodynamics chapter. Okay, and this is your, according to your syllabus for BTech first year course. Okay, so what we discussed till now, this all the discussion or all the topics are included in the BTech first year course of the chemistry syllabus. So that's all for today. Next class we will discuss about the little bit electrochemistry, because Nernst equation is also included in your syllabus. So meet with you in the next class. Goodbye, take care, and thanks for watching.